Hi everyone. So we continue from what we stopped last time. So last time we stopped from pooling effect sizes. We talked about effect size measures in continuous outcomes, and we have already covered. Actually, come far away from what we have started. So we have at this point, I believe you have a very good understanding of effect size measures in binary and continuous outcomes. So what is left is dealing with a theoretical understanding of the pooling effect size methods. So today we want to. I'm going to talk about pooling effect sizes, and we will go through the effect size method mainly, and in the next session we'll talk more on random effects meta-analysis. But for today we'll talk about fixed effect meta-analysis. So the basic idea behind fixed effect and random effects model is a model. So what is a model? So when we look at a model, the philosophical idea behind the model is to actually explain reality. That's what a model does. So you want to explain the truth. You want your model to explain that reality as approximately as good as possible. You cannot explain, you cannot really get the truth, but still you try to approximately measure it. That's what the basic idea behind the model. And as we know, there is true effect size which is hiding in the population that we are trying to measure. And how many true effect sizes are hiding in the population? There is only one true effect size. But the only way we measure it is we take samples and then we try to measure it. So how much so let's say if you measure one effect size and then you try to measure another effect size, and so let's say you have many different effect sizes. And the question is, how much do these observed effect sizes actually vary from one study to the other? So that means you take one sample and then you have one effect size. So that means there is between sampling difference. So there is always all studies attempted to measure the true effect size that's actually hiding in the population. So you don't know what that true effect size is, but you try to measure it. And the way we measure it is we design a study and we try to measure that effect size with theta, and that is with some kind of error. So that means the observed effect size of some study K is actually an estimator of the true effect size, which is burdened by the study sampling error. That's what the observed effect size that's actually trying to tell you. But the main goal is to measure this true effect size, which is hiding in the population. So let's go to fixed effect model. So as I said, we have two main philosophies in meta-analysis. One is a fixed effect model, and the other one is a random effect model. So the fixed effect model. It says observed effect size may vary. They may vary from one study to the other, but it assumes this is only because of the sampling error. So that means the main difference between this observed effect size, the main difference or the main variation behind this difference is, so it assumes it's because of the sampling error. So that means in reality, their true effect sizes are all the same. That means the true effect size they try to measure is the same, but there is a difference in their sampling. So that is sampling error. So the true effect size, you try to measure it by theta, and then, as we said, this true effect size that you try to measure by the observed effect size, so there is always some kind of error. So if you measure the true effect size by this observed effect size, there should be something to measure the error, and that's its with sampling error, and that's actually statistically estimated by the standard error. That's the basic idea behind this observed effect size and its relationship with the true effect size. So that means if you do like this kind of simulation study and you have many different effect size measures, so you try to take many samples, as many as you can, and then you try to measure the true effect size, which is actually lying here on 0. So that means, and then on the y-axis there is a standard error. So as the standard error gets bigger and bigger, so that means the true effect size, the observed effect size will stay far away from the observed effect size. So here, let's say in this case, the standard error is small. That means the true effect size, the observed effect size is actually close to the mean effect size. But in the other ways, in the other sectors here on this side and on this side, you see the standard error is high or big. So that means they are far away from the true effect size. So studies with a smaller standard error, so that means as we have seen in the previous picture, so studies that have a smaller standard error have always a smaller sampling error. And that means their estimate of the overall effect size is therefore more likely actually to be close to the true effect size that they are actually aiming to measure. And we know they have different standard error and different degree of distance from their intended goal of measuring the true effect size. So that means you have many studies measuring different effect size, and they all have some kind of distance from the true effect size measure. And so we want to average. We want to pool these studies. So if you actually aggregate all these studies, so that they will be close to the mean and the true effect size. That means which is like here. So if you aggregate all of them, so you will be able to still approximately measure with the true effect size. So the problem is, how do we average these studies? So you have many studies, you want to average, and you want to synthesize, you want to pool them. So one idea is take a weighted average of all of the studies. Take a weighted average of all of these studies. But how do we calculate this? How do I calculate the weighted this weighted average? How do you calculate the weight? the main thing that you take is takes the inverse variance, which is the inverse of the variance. That means, so you weight the power of the studies by this amount. So that's how you actually average them. Now, how do I combine all of them? The way to combine all of them is simple. So the only way to combine is, so let's say you know this one, you know this formula. This is arithmetic mean. So that means the summation of all xi's divided by the number of the total number of observations. That's how you calculate the mean. But if you want to calculate the weighted effect size, I mean the weighted mean of this effect size, that means you multiply this by the weight of each study. So that means you will do this. So the summation of each study multiplied by the weight divided by the total number of weights will give you the pooled effect size measure. That's how you calculate the, how you synthesize, how you pool all the studies. That's all for now, and next is to jump into the practical session. So I will open R and I will show you how you do the fixed effect model, and we will manually calculate all of this, and I will show you how you calculate the weight, and I will show you how you pool the studies all together. So let me just open R, and I will directly proceed to the practical thing. Let me just go and open my R. So my R is here. So here I have my R Studio. So maybe because I already calculated a little bit. So let me just remove this, and then we will. So for this for pulling for this part, we need fixed effect meta-analysis, and for that we obviously need data, and for the data maybe we need d-meta actually. So maybe if you know, if you install metan package, it's always nice if you also install d-meta function if you want to learn something, because this d-meta actually contains some data which we can also use. And the other function, the other package that I want to use is meta, and I think I don't need anything else. The other ones I will simply I'll simply calculate. So for this, let me, d-meta has actually a data which is called suicide prevention. So let me attach that data. So let me just check the suicide prevention. So there is this data which is called suicide prevention. So let me just attach that data in our so, and then let's have a look what that data actually looks like, how that data looks like. So then let me just simply see the structure of that data and see some of the variables. Actually, we can also view it instead. So we can view it in my window here, and then we see what data looks like. So this is how the suicide prevention data looks like. So they are trying to do this randomized control trial, I would say. So there is these are the authors, and here are the number of people in the experimental group, and the mean, the standard deviation, number of people in the control group, and the mean in the control group, and we also have the standard deviation. These are actually basically what we need for pooling effect sizes. So this is once you have this, and then the rest is simply replacing, substituting from the equation. So we go back to our markdown file, and then we try to measure the weight. So first thing that you need to do, if you remember, we have said that we measure the inverse variance. So for the inverse variance, actually the first thing is we need to calculate the variance of the studies. The way you calculate the variance is actually by okay, maybe I should there is one formula up here that we have already covered in the past. Maybe we can so this is so you have a standard error. This is how you measure the variance. So you have S squared n1 1 over n1 plus 1 over n2, and then you get the variance. So this is how you calculate the variance. So, and then you square it, and then you get the variance. That's what we need. So for that, so I need with function, or you can also do it. I just don't want to do this dollar sign because it's a little bit time taking. So I will just do the with function, and then I will call my suicide prevention data, and I will simply remember those the suicide prevention. I have NE, ME, SDE. So for the variance, what I need is like I need a standard deviation, and then the total number of people in the both experimental and control group. I think that's all what I need. So with suicide prevention, and then I call my data, and then afterwards I write an equation how to calculate the variance. The way I calculate the variance is I calculate the standard error, and I square it. I square that value. So let me call this, and then once I square it, I divide that one with an experimental group. Then after that I plus 2, and then for the control group. So then I will simply call that function, the same function, but now it's for the control group. I will simply change this to MC, and now I should be good to go. Now I should have my variance. So that means instead of square root of, so now because I need variance, this is a pooled standard, actually the pooled standard deviation formula, and then when you square it, you get the variance. So let me just, now it seems I have one bracket missing, and okay, there seems to be, okay, now here, and maybe I don't need this. So we have here standard deviation in. Okay, let me just put all of these things here, and actually this is what I need. And then standard deviation in. Also this one. Okay, Okay, let me put again this one in bucket. Now I should be able to find my variance. So let me just calculate here. Okay, so there seems to be some bucket. Let me actually put this standard deviation E squared divided by NE plus standard deviation C squared divided by NC. Yeah, I think I should be okay now. So now it should work. Unless I made a mistake, but we will check. So here we have the variance, and we have the variance values for each studies. So we already have that. And then the other thing that we need is like I need to calculate the weight, and the weight would be the inverse variance. And that one, the way you calculate is simply take the inverse of that variance. The variance that we just calculate, that's the weight of each individual studies. Now if I print, I should be able to get the weight of studies, each study. So this is how each studies contribute. But we want to make it percentage. If you want to make it how that percentage, how much percent this value actually contributes, then what you do is like you weight the weight of, I mean that's the inverse variance divided by the sum total of those inverse variance. That means sum weight, and then you multiply that number with by 100. So and then after that, if I multiply by 100, so that means I have this study contributes a weight of 6%. That's how you calculate the weight by percentage. But now I simply calculate the inverse variance. That means that's the weight. I didn't calculate the percentage weight, but this is the value that I need for for calculating the weight total. The other thing that I need is I need to calculate the weight total, and for that I simply sum the weight. That's how I calculate the weight total. Then afterwards, I need to calculate the standard error. The standard error is calculated as standard error is 1 over the weight. So you say variance is actually standard error. So the way you calculate is just moving this equation here and moving the weight here. So that means 1 over square root of sum weight. That would be our standard error for the entire study. Actually, if I want to calculate confidence interval or something, this is the value that I need later on. And then let's have a look. Let's have a look again how this looks like. So now there seems to be, I must have made some error here. This is a square root, not SRT. Now I have the standard error. So the standard error is about, no, I didn't print it, but if I print it, I should have one value. That's the standard error that I have. That's a standard error. So the next thing is I need to pull. Now I have, if you remember, so I have this formula. If you go to the very end of the slide, so I have now the weight, I have the theta for each studies, I have the weight for each studies, and then I have the sum, the weight total. Now I should be able to calculate this theta, that means the full effect size, using the fixed effect size, the fixed effect rate actually. So that's how I calculate it. Then now I have the standard error, and then the last thing that I need to do is effect size. Effect size, the way I calculate it, so again, let me simply call my loss function, and then suicide prevention. And once you call the suicide prevention, I can simply, first thing actually I need to calculate the effect size. The way you calculate the effect size is like the individual effect size, because we don't have the individual effect sizes yet. So I have mean in the experimental group, and then I have mean in the control group. The effect size measure that we want is the mean difference, of course, because this is continuous outcome. But if we assume that all this depression, all these measures, they are measured with some exactly similar variable. So that's why we are using this mean difference. Otherwise, we have to use standardized mean difference. But I'm just assuming that these all these studies, they measure depression with the same outcome. So that's why I'm trying to rule them with a mean difference. So that means I will call my mean experimental group minus the mean in control group. That's how I calculate my effect size. So now I have a standard error. Actually, this should have been the first thing that I have to calculate, because once you have the effect size, and then afterwards you calculate the standard error, and then from there you calculate your weight, and then the full effect size, and then later your confidence interval. Yeah. So now I should be able to calculate my effect size. That means effect size for each study. You can also calculate it this way. That means effect size equals suicide prevention mean minus mean experimental group minus that one. That would also should give you the same result. This one here, mean instead C. Let me calculate it this way, and let me take it down here in the console, and let me show you. It should be the same. So now I have, these are the effect sizes, the individual studies. That is study 1, study 2, study 3, and 4, and until the last one. So these are the effect sizes. But I would prefer to, because I don't want to use this dollar sign. But you can also use other methods like deploy or those kind of package. But I just want to do it this way. I found it easy. Then effect size, I should be able to get the same kind of effect sizes that we have seen here. Now let me run it again. Now I should be able to get the same effect size measures actually, like we have seen here. So you see, we have already calculated. Now, if you remember, let me remind you. Here is the way we pull effect sizes by using the fixed effect measure. Then we have the summation of individual observed effect size times their weight divided by the sum total of their weight. For that, simple. Let me call this pooled effect size. Let me call it pooled full effect size, and then that one, the way I calculated is like I need to sum the effect size times the effect sizes here, the individual effect sizes, and then I multiply them by weight, by each individual weight, and then finally I divide it by summation of the weight sum. That means the weight total. That's exactly this formula is actually similar to what we have seen here. So now I should be able to get the pooled effect size measure. So if I print it here, and you will see the effect size, the pooled effect size measure. That means the pooled value. So this is my effect size. You can round it. Maybe let me round it to 3 digits if I want. So let me put it 4 digits. Okay, let me put it to 4 digits. Then we should be able to see that effect size, the pooled effect size. Round. This is supposed to be round. Actually, that should be about 3.597. That's our effect size. Now, if I want to calculate the confidence interval, the way you calculate is you take the pooled effect size measure. I think you know how to calculate effect size. I mean, confidence interval. You take the z alpha over 2, that means 1.96, times the square root of the standard error, which is the summation of the variance that we have seen. That is the standard error, which we have already mentioned here. That's standard error, this one. And with that, we should be able to, that's one. And the other one is, that's one, the upper limit. And the lower limit would be minus. That would be our lower limit. Let me start with the lower limit, and then afterwards let me start with another limit. Maybe let me call this one lower, and upper, and then let me paste. Lower with upper. And now I should be able to. Actually, I can also put the effect size. If you want, you can see effect size here. The pooled actually, that's range. And let me just drop it here and pull all of them. That means the full effect size, the lower limit, and the upper limit. That's the 95% confidence interval. Now I should be able to see all of these values. So now it's really large, but maybe it's better to round them, maybe to 4 digits. Let me just put it to 4 digits. And again, here again, round 4 digits. And let me again round this one again, round 4 digits. And afterwards, let me just remove this one, and now we should be able to see them in 4 digits. Okay. Okay, could not function round. Where, yeah, this one. I made an error here. And now if I run this, I should be able to get that confidence interval. Oh, okay. There seems I must have made a mistake somewhere here. So because the upper it shouldn't be like this. This is a bit high. Okay. Okay. Standard error. That's actually the standard error that I want. Maybe I just put it here. Now it should work, because that's actually the value that I want. So square root of 1 over square root of some weight. That's my standard error. Now it should be. We should be fine. It should be. Okay. The lower it's saying minus 1.0. Okay. Anyway, let's see. Okay. This is the sum val. That means the variance, the summation of the variance is a standard error. The standard error that I want. So that means weight total. Okay. Okay, something's wrong here. But that would be the same as what I did. No, this can't be right. Oh, no, not this one. This is actually the value we want. The value we want is this standard error. So that's the standard error is 0.13. This is the value we want. So that means we just need to, where did I calculate? I calculated it here. So it should be round sum effect size times weight over some weight. Now this is the pooled effect size. We already get the pooled effect size. Now the standard error. That's the one we have. Because when you calculate the standard error, you have the mean plus or minus the 1.96 times the square root of standard error. That's how you usually calculate your confidence interval. And the same should be here. So standard error. Now it should be able to get the right confidence interval. Otherwise, something must be wrong in the previous calculations. Yeah, well, it's still there is a problem. Okay, since I is it with the square root? Let me just check. try it with that, but I probably forgot this confidence interval formula just for a moment. Yeah, okay, it should not be standard error. Okay, it should not be in the square root, so it should be not in the square root. So that means it's like x plus x bar, that means the mean plus or minus 1.96 times the standard error, not the square root of standard error. I made a mistake. So that's where we made error. So the confidence interval would be here. So that means you see the point estimate, that means the pooled effect size is here, and then the and then you see. So now you can also calculate the z-score. If you want to calculate the z-score, that means you simply divide the pooled effect size measure divided by what was this? The standard error. So you simply z-score would be divided by standard error. That's how you would calculate the z-score. But if you really want to calculate the p-value or something, but this is how you would calculate the z-score. Now I show you the same. This is how we manually would calculate. This was a bit tedious, so that will be our z-score value. But when you see the confidence interval, it doesn't include 0. So it's like from minus to minus 0.08, so it doesn't touch 0. So that means the pooled effect size is significant. It's so it's on the left side of the plot. So that means you see that one. So this is how you manually calculate. But if you want to make it quick, you simply load your meta function, the meta package. You already have the meta, you already loaded it, and you simply call the metcont for continuous autocam, and then you call NE, and that means the number of people in the experimental group, and the mean E, and then for also the that means the standard deviation again you have to call, and then the same for the control groups. That means NC times mean C and SPC. Then afterwards you can give the data. The data will be our suicide prevention data, suicide prevention, and then afterwards you simply give the effect size measure. That means we are using mean difference. Now we should be able to find the same confidence interval and the same this estimates. We should be able to find them. So if I run this again, maybe I create another cell. I think it's better. So I create another cell. So to create another cell here, I simply Control Alt I gets this. Now I can simply with just quick method, random fixed effects meta-analysis. It actually also gives us the random and both the fixed and the random effects. So this is you simply call your metacont function, and then this is exactly what we have actually calculated. Also, we have already calculated the z-score. If you remember, we have already 2.57. This is 2.57 roundabout, and the p-value will be just looking table, and then you get this this p-value. So again, you see the confidence interval. Our confidence interval, the one we calculated, is exactly like this, so 0.6341 until 0.853, and random effects meta-analysis we haven't calculated. We are using so that's how you would calculate, how you would synthesize if you want to do it manually. But again, you spend all of these lines of code, but with the package it's just with this you can rule everything. But if you want to see how the forest plot looks like, you can simply call the forest function. We will come back to this, no rush. But then if I simply pass that to forest plot, I see this kind of forest plot. Maybe it's better to see it in the console instead. I mean, in the viewer window. Here on the plot window, and then we can zoom it and see how it looks like. So I can do more, of course, more to label the studies by the study ID, and this one we will see it later in the future. So this is how our effect size looks like, and that's how we calculate it manually, and that's the goal of my session today. I hope you enjoy this. Next, we'll talk more on random effects meta-analysis and and other aspects of the meta-analysis. Maybe let me go back to this and show you something. So if you remember the metacont function, it gives us many different outputs. The first one is the number of studies and number of observations. That means the total number of people who were included in the study. And then it gives you the fixed effects model. That's actually a better name, common effects model. Then the random effects model. And it gives you the confidence interval, the z and the p-value. And after that, they give you the heterogeneity statistics, which is measured by tau square and then I square value. And then it gives you some of this. You can roughly calculate all of this manually if you want. Maybe I will show you in the future how you can do that. I think that's all for today. Thank you for watching, and I hope you will continue. Thank you very much.